Okay. So to quickly summarize, we have started into neural networks, and neural networks is basically so far as we are saying, it's a supervised learning algorithm where the structure of learning is based upon layered components called neurons. So everything is a neuron, starting from input layer to hidden layers to output layers. What a neuron is basically is an object to store number, and it is connected to other neurons using weights. So every element of the input layer will be connected to the next layer using series of weights, and additionally a bias term. And then every neuron of the next layer will be connected to the other layer, the next layer, using again a series of weights and a bias layer. So this happens all the way till the end, and our hope is that this complicated structure with a huge number of connections will be able to learn concepts or patterns in a more intuitive way. Okay. We hope that the layered approach works using a series of abstractions. So let's say here in our case, when we are trying to solve the interesting task of identifying handwritten digits, our hope is that each of the pixels that go into the first layer, that is for a 28 by 28 image, we get 784 inputs for the first layer. We hope that the next layer, the first hidden layer, will be able to capture small bits and pieces, that is edges of the numbers. The next layer will be able to combine these edges into interesting patterns like straight lines and loops and so on. And the next layer we hope will be able to combine these higher concepts into numbers. Okay. We saw that the way that we can go from the input layer to the output layer is called the feed forward, where basically we are just evaluating this network. That is, any input that comes in, which comes in the value from 0 to 1, will be multiplied to their corresponding weights, and uh, they'll be summed together, and it is passed through a sigmoid function which squishes the entire range of input to a value between 0 and 1, and this value between 0 and 1 represents the activation of this neuron. So we go from input layer to the next layer, from the first hidden layer to the second hidden layer, and from the second hidden layer to the output layer using the same strategy. Once we reach the output layer, we have 10 neurons, and our hope is that when we started with an image of, let's say, 3, the number corresponding to 3, the neuron corresponding to 3 will light up, okay, and everything else will be dark. And initially, since we start with the random weights, we know that that cannot happen and it may not be true. Then we have to provide an error and give a sense of what was wrong, so that the model can rectify its mistake. So that we do using a process called as backpropagation, and the backpropagation uses something called as gradient descent to work this out. We also compared gradient descent with what we did in linear regression, which ultimately comes to finding the value, or what are the weights and parameters that we should set so that the unit cost becomes lowest, so that the cost becomes lowest, and that is our hope. And for that we use gradient descent, which basically gives you the slope at every point. Once you have the slope, you can travel towards the negative of that slope, so that you are reducing the cost. And once we are reducing the cost, we come to a point where the weights don't change any longer. And since the weights don't change, we say that we have reached the minimum cost. That is, our network is now optimized. That means that with these trained values of parameters, when we pass an input, we should expect the right output getting right. Okay. So that was the context. We had reached, I guess, video 2 in this part. So I've already taken it a little back. We'll play from here. And if you have any questions, we can stop and discuss. Let's see how it goes. Okay. Even before starting, do you have any questions? Okay. In that case, let me play. Let's start this.
Then when the slope is flattening out towards the minimum, your steps get smaller and smaller, and that kind of helps you from overshooting. Bumping up the complexity a bit, imagine instead a function with 2 inputs and 1 output. You might think of the input space as the xy plane, and the cost function as being graphed as a surface above it. Now, instead of asking about the slope of the function, you have to ask which direction should you step in this input space so as to decrease the output of the function most quickly. In other words, what's the downhill direction? And again, it's helpful to think of a ball rolling down that hill. Those of you familiar with multivariable calculus will know that the gradient of a function gives you the direction of steepest ascent. Basically, which direction should you step to increase the function most quickly? Naturally enough, taking the negative of that gradient gives you the direction to step that decreases the function most quickly. And even more than that, the length of this gradient vector is actually an indication for just how steep that steepest slope is. Now, if you're unfamiliar with multivariable calculus and you want to learn more, check out some of the work that I did for Khan Academy on the topic. Honestly though, all that matters for you and me right now is that in principle there exists a way to compute this vector. This vector that tells you what the downhill direction is and how steep it is. You'll be okay if that's all you know and you're not rock solid on the details. Because if you can get that, the algorithm for minimizing the function is to compute this gradient direction, then take a small step downhill, and just repeat that over and over. It's the same basic idea for a function that has 13,000 inputs instead of 2 inputs. Imagine organizing all 13,000 weights and biases of our network into a giant column vector. The negative gradient of the cost function is just a vector. It's some direction inside this insanely huge input space that tells you which nudges to all of those numbers is going to cause the most rapid decrease to the cost function. And of course, with our specially designed cost function, changing the weights and biases to decrease it means making the output of the network on each piece of training data look less like a random array of 10 values and more like an actual decision that we want it to make. It's important to remember, this cost function involves an average over all of the training data. So if you minimize it, it means it's a better performance on all of those samples. The algorithm for computing this gradient efficiently, which is effectively the heart of how a neural network learns, is called backpropagation, and it's what I'm going to be talking about next video. There, I really want to take the time to walk through what exactly happens to each weight and each bias for a given piece of training data, trying to give an intuitive feel for what's happening beyond the pile of relevant calculus and formulas. Right here, right now, the main thing I want you to know, independent of implementation details, is that what we mean when we talk about a network learning is that it's just minimizing a cost function. And notice, one consequence of that is that it's important for this cost function to have a nice, smooth output, so that we can find a local minimum by taking little steps downhill. This is why, by the way, artificial neurons have continuously ranging activations, rather than simply being active or inactive in a binary way, the way that biological neurons are. This process of repeatedly nudging an input of a function by some multiple of the negative gradient is called gradient descent. It's a way to converge towards some local minimum of a cost function, basically a valley in this graph. I'm still showing the picture of a function with 2 inputs, of course, because nudges in a 13,000 dimensional input space are a little hard to wrap your mind around, but there is actually a nice non-spatial way to think about this. Each component of the negative gradient tells us 2 things. The sign, of course, tells us whether the corresponding component of the input vector should be nudged up or down. But importantly, the relative magnitudes of all these components kind of tells you which changes matter more. You see, in our network, an adjustment to one of the weights might have a much greater impact on the cost function than the adjustment to some other weight. Some of these connections just matter more for our training data. So a way that you can think about this gradient vector of our mind-warpingly massive cost function is that it encodes the relative importance of each weight and bias. That is, which of these changes is going to carry the most bang for your buck. This really is just another way of thinking about direction. To take a simpler example, if you have some function with 2 variables as an input, and you compute that its gradient at some particular point comes out as 3, 1, then on the one hand, you can interpret that as saying that when you're standing at that input, moving along this direction increases the function most quickly. That when you graph the function above the plane of input points, that vector is what's giving you the straight uphill direction. But another way to read that is to say that changes to this first variable have 3 times the importance as changes to the second variable. That at least in the neighborhood of the relevant input, nudging the x value carries a lot more bang for your buck. Alright, let's zoom out and sum up where we are so far. The network itself is this function with 784 inputs and 10 outputs, defined in terms of all of these weighted sums. The cost function is a layer of complexity on top of that. It takes the 13,000 weights and biases as inputs and spits out a single measure of lousiness based on the training examples. And the gradient of the cost function is one more layer of complexity still. It tells us what nudges to all of these weights and biases cause the fastest change to the value of the cost function, which you might interpret as saying which changes to which weights matter the most. So, when you initialize the network with random weights and biases and adjust them many times based on this gradient descent process, how well does it actually perform on images that it's never seen before? Well, the one that I've described here, with the 2 hidden layers of 16 neurons each, chosen mostly for aesthetic reasons, well, it's not bad. It classifies about 96% of the new images that it sees correctly. And honestly, if you look at some of the examples that it messes up on, you kind of feel compelled to cut it a little slack. Now, if you play around with the hidden layer structure and make a couple tweaks, you can get this up to 98%. And that's pretty good. It's not the best. You can certainly get better performance by getting more sophisticated than this plain vanilla network. But given how daunting the initial task is, I just think there's something incredible about any network doing this well on images that it's never seen before, given that we never specifically told it what patterns to look for. Originally, the way that I motivated this structure was by describing a hope that we might have. That the second layer might pick up on little edges, that the third layer would piece together those edges to recognize loops and longer lines, and that those might be pieced together to recognize digits. So, is this what our network is actually doing? Well, for this one at least, not at all. Remember how last video we looked at how the weights of the connections from all of the neurons in the first layer to a given neuron in the second layer can be visualized as a given pixel pattern that second layer neuron is picking up on? Well, when we actually do that for the weights associated with these transitions from the first layer to the next, instead of picking up on isolated little edges here and there, they look, well, almost random, just with some very loose patterns in the middle there. It would seem that in the unfathomably large 13,000 dimensional space of possible weights and biases, our network found itself a happy little local minimum that, despite successfully classifying most images, doesn't exactly pick up on the patterns that we might have hoped for. And to really drive this point home, watch what happens when you input a random image. If the system was smart, you might expect it to either feel uncertain, maybe not really activating any of those 10 output neurons or activating them all evenly. But instead, it confidently gives you some nonsense answer, as if it feels as sure that this random noise is a 5 as it does that an actual image of a 5 is a 5. Phrased differently, even if this network can recognize digits pretty well, it has no idea how to draw them. A lot of this is because it's such a tightly constrained training setup. I mean, put yourself in the network's shoes here. From its point of view, the entire universe consists of nothing but clearly defined unmoving digits centered in a tiny grid, and its cost function just never gave it any incentive to be anything but utterly confident in its decisions. So with this as the image of what those second layer neurons are really doing, you might wonder why I would introduce this network with the motivation of picking up on edges and patterns. I mean, that's just not at all what it ends up doing. Well, this is not meant to be our end goal, but instead a starting point. Frankly, this is old technology, the kind researched in the 80s and 90s. And you do need to understand it before you can understand more detailed modern variants, and it clearly is capable of solving some interesting problems. But the more you dig into what those hidden layers are really doing, the less intelligent it seems. Shifting the focus for a moment from how networks learn to how...
Okay, so let me summarize so far. So what he has introduced is we saw how gradient descent works for a single dimension or two dimensions, but when we move towards the 13,000 variable dimensions, what you could think that gradient descent is doing is not just talking about value or not just talking about direction, but also talking about something like what the weights need to be updated as. Okay, so we see that each gradient descent multiplication, it turns out to be either a positive or a negative number, and it has a relative magnitude. And what that relative magnitude suggests is that changes to this particular weight, if it has a high relative magnitude, changes to this particular weight matters to us more than changes to another variable whose value is lesser. Okay, and that is a good way of at least visualizing or understanding what our model is supposed to do or what it is doing. Additionally, he talked about this point where initially he started the layered approach and telling that how it would break down into structure, and when we actually see it for this neural network, the multi-layer perceptron, what we find out is that is not exactly what it does. And then one way to imagine that is thinking this, because our cost function and our problem is so complicated that within this entire space there exists local minimas that allow us to solve the problem, but not for the same reasons that we had thought. Okay, the reasons that we would think as humans is not the reason that the network has found out. It has found out some solution, and they may be local minimas, because of which it is able to still predict the right answer. And thus, when we look at the plots of these hidden layers in between, we are not able to recognize any patterns. Okay, but since he said one more thing, that this idea is useful because multi-layer perceptron is just the starting point of neural networks. When we go to more advanced algorithms like CNNs, computational neural networks, and LSTMs, long short term memory, such kind of networks, this idea is very useful because it helps us to at least understand or give an insight of how the network may be solving things. Okay, let me go ahead. Do you have any questions at this point? Okay, let me go ahead.
You learn? That'll only happen if you engage actively with the material here somehow. One pretty simple thing that I want you to do is just pause right now and think deeply for a moment about what changes you might make to this system and how it perceives images if you wanted it to better pick up on things like edges and patterns. But better than that, to actually engage with the material, I highly recommend the book by Michael Nielsen on deep learning and neural networks. In it, you can find the code and the data to download and play with for this exact example, and the book will walk you through step by step what that code is doing. What's awesome is that this book is free and publicly available, so if you do get something out of it, consider joining me in making a donation towards Nielsen's efforts. I've also linked a couple other resources that I like a lot in the description, including the phenomenal and beautiful blog posts by Chris Olah and the articles in Distill. To close things off here for the last few minutes, I want to jump back into a snippet of the interview that I had with Lisha Lee. You might remember her from the last video. She did her PhD work in deep learning.
Okay, maybe before going there, he talked about this concept, right? To stop and ponder how we can probably make the network learn the way that we want it to see. Okay, that is learning in edges and patterns. Okay, do you have any idea on this, or any comments on why do you think the network is not learning the way we think? Why is it learning something random?
If we increase the pixel rate, it will be better, right?
Mm-hmm.
I think the answer is wrong, but still, I just want to make that.
Pixel, what he's saying is if we increase, so instead of 28 by 28, if we go for more number of pixels,
Yeah,
okay, yeah, and nonetheless, the randomness that we talked about by this will not change, right?
yeah.
Yeah. So increasing pixels would basically say more number of inputs, and especially for this problem, you would have to analyze. You would have to think. Uh, can I solve this problem using less pixels? And if I can solve this problem using less pixels, then I have less number of weights and parameters to learn, which means a simpler system to solve, right? So it is more manageable. If you go for a high pixel rate or high resolution, that would increase the complexity, thereby making it more difficult to learn. So again, depends upon if the actual image is able to represent the picture or not. So in this case, for numbers, this is fine. But if you have to say these are for 28 by 28 pixel, 28 by 28 image of faces of people, then it will be a difficult, hard problem, because with 28 by 28, difficult to see lines and edges on a face and so on. For numbers, I think this is fine, right? Okay. Maybe I'm more interested in the first question. Why is the network picking out something random to look at? And why not it is giving us the patterns that we want? So one way to analyze it is this. What we have done is when we look at our input layer, we see 784 different inputs. And these 784 different inputs, when I say what is the link between input 1, input 2, input 3, then I can say these 3 inputs are in one line at least. Okay, 1, 2, 3. But once I reach 28 lines, 28 inputs, and then I go back to the first one, then the link, the link that should be there between the first and, so normally when you look at images, you look at groups of pixels close to each other, right? So let's say when I make a circle like this, when I make a box like this, I'm looking at groups of pixels as at one go. I am not really concerned when I'm looking at this box what is happening somewhere here, or what is happening somewhere here, or what is happening somewhere here. I'm more interested to see them as groups of pixels, and that groups of pixels helps me identify patterns. Does that make sense? So if I hope that my network will learn edges and things like that, and in the next layer it will learn combinations of these edges, then I have to provide inputs as groups of these patterns, not as single lines that go 28 inputs here, then 28 inputs to the next line, next 28 from the next line, and so on. So this approach of looking at pixels like a group and then working on such groups is basically the starting point of the next neural network that you could look at, is convolutional neural networks. Okay, so here we look at different sizes of these boxes. So a small box basically means lower dimension analysis. A big box means higher dimension analysis. So I think that's an interesting discussion of why this happens and how this can be done. Nonetheless, if you don't understand this, it is totally fine. We don't need to know this to get ahead. Okay. Let us see what he discusses with the researcher. Do you have any questions, or should I go ahead? Okay, I'll go ahead.
You might remember her from the last video. She did her PhD work in deep learning. And in this little snippet, she talks about 2 recent papers that really dig into how some of the more modern image recognition networks are actually learning. Just to set up where we were in the conversation, the first paper took one of these particularly deep neural networks that's really good at image recognition, and instead of training it on a properly labeled dataset, it shuffled all of the labels around before training. Obviously, the testing accuracy here was going to be no better than random, since everything's just randomly labeled. But it was still able to achieve the same training accuracy as you would on a properly labeled dataset. Basically, the millions of weights for this particular network were enough for it to just memorize the random data, which kind of raises the question for whether minimizing this cost function actually corresponds to any sort of structure in the image, or is it just, memorization?
Memorize the entire data set of what the correct classification is. And so a couple of, half a year later at ICML this year, there was not exactly a rebuttal paper that addressed some aspects of like, hey, actually these networks are doing something a little bit smarter than that. If you look at that accuracy curve, If you were just training on a random data set, that curve sort of went down very, very slowly in almost kind of a linear fashion. So you're really struggling to find that local minima of possible, the right weights that would get you that accuracy. Whereas if you're actually training on a structured data set, one that has the right labels, you fiddle around a little bit in the beginning, but then you kind of dropped very fast to get to that accuracy level. And so in some sense, it was easier to find that local maxima. And so what was also interesting about that is it brings into light another paper from actually a couple of years ago, which has a lot more simplifications about the network layers, but one of the results was saying how if you look at the optimization landscape, the local minima that these networks tend to learn are actually of equal quality. So in some sense, if your data set is structured, you should be able to find that much more easily.
My thanks, as always, to those of you supporting on Patreon. I've said before just what a game changer Patreon is.
Yeah, just to quickly summarize on or comment on this learning that we found here. What this basically suggests is if you are providing structured data, most of your cost, most of your local minima will end up at the same point. And the advantage of that is even though when you train different networks, so let's say with the same data and same configuration, I train a network on my system and Anand trains a network on his system, Srinivas trains a network on his system, Svecha trains a network on her system, that even though we may have different weights, it is very likely that all of our algorithms with the same setup will work equally better. Okay, we may all maybe end up at different local minimas, but those local minimas will be sufficient enough to give us the same level of accuracy. And that's an interesting observation. That's an interesting outcome of the neural networks. So it doesn't, so the weights and biases, even though individually they're important, but collectively what we get out of that is not as important than the final answer that we get out. Okay. Again, if you don't understand this part, it is totally fine. Okay, and it is not important for implementing neural networks. Let me then start the next video. So this probably will be the most important video because we are learning how backpropagation works.
Here, we tackle backpropagation, the core algorithm behind how neural networks learn. After a quick recap for where we are, the first thing I'll do is an intuitive walkthrough for what the algorithm is actually doing, without any reference to the formulas. Then, for those of you who do want to dive into the math, the next video goes into the calculus underlying all this. If you watched the last two videos, or if you're just jumping in with the appropriate background, you know what a neural network is, and how it feeds forward information. Here we're doing the classic example of recognizing handwritten digits, whose pixel values get fed into the first layer of the network with 784 neurons, and I've been showing a network with 2 hidden layers having just 16 neurons each, and an output layer of 10 neurons, indicating which digit the network is choosing as its answer. I'm also expecting you to understand gradient descent, as described in the last video, and how what we mean by learning is that we want to find which weights and biases minimize a certain cost function. As a quick reminder, for the cost of a single training example, what you do is take the output that the network gives, along with the output that you wanted it to give, and you just add up the squares of the differences between each component. Doing this for all of your tens of thousands of training examples and averaging the results, this gives you the total cost of the network. And as if that's not enough to think about, as described in the last video, the thing that we're looking for is the negative gradient of this cost function, which tells you how you need to change all of the weights and biases, all of these connections, so as to most efficiently decrease the cost. Backpropagation, the topic of this video, is an algorithm for computing that crazy complicated gradient. And the one idea from the last video that I really want you to hold firmly in your mind right now is that because thinking of the gradient vector as a direction in 13,000 dimensions is, to put it lightly, beyond the scope of our imaginations, there's another way you can think about it. The magnitude of each component here is telling you how sensitive the cost function is to each weight and bias. For example, let's say you go through the process I'm about to describe and you compute the negative gradient, and the component associated with the weight on this edge here comes out to be 3.2. while the component associated with this edge here comes out as 0.1. The way you would interpret that is that the cost of the function is 32 times more sensitive to changes in that first weight. So if you were to wiggle that value just a little bit, it's going to cause some change to the cost, and that change is 32 times greater than what the same wiggle to that second weight would give. Personally, when I was first learning about backpropagation, I think the most confusing aspect was just the notation and the index chasing of it all. But once you unwrap what each part of this algorithm is really doing, each individual effect that it's having is actually pretty intuitive. It's just that there's a lot of little adjustments getting layered on top of each other. So I'm going to start things off here with a complete disregard for the notation, and just step through those effects that each training example is having on the weights and biases. Because the cost function involves averaging a certain cost per example over all the tens of thousands of training examples, the way that we adjust the weights and biases for a single gradient descent step also depends on every single example. Or rather, in principle it should, but for computational efficiency, we're going to do a little trick later to keep you from needing to hit every single example for every single step. In either case, right now, all we're going to do is focus our attention on one single example, this image of a 2. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random, maybe something like 0.5, 0.8, 0.2, on and on. Now we can't directly change those activations, we only have influence on the weights and biases. But it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we want it to classify the image as a 2, we want that third value to get nudged up, while all of the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase to that number 2 neuron's activation is in a sense more important than the decrease to the number 8 neuron, which is already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer, plus a bias, which is all then plugged into something like the sigmoid squishification function, or a ReLU. So there are 3 different avenues that can team up together to help increase that activation. You can increase the bias, you can increase the weights, and you can change the activations from the previous layer. Focusing just on how the weights should be adjusted, notice how the weights actually have differing levels of influence. The connections with the brightest neurons from the preceding layer have the biggest effect, since those weights are multiplied by larger activation values. So if you were to increase one of those weights, it actually has a stronger influence on the ultimate cost function than increasing the weights of connections with dimmer neurons, at least as far as this one training example is concerned. Remember, when we talk about gradient descent, we don't just care about whether each component should get nudged up or down, we care about which ones give you the most bang for your buck. This, by the way, is at least somewhat reminiscent of a theory in neuroscience for how biological networks of neurons learn, Hebbian theory, often summed up in the phrase, neurons that fire together wire together. Here, the biggest increases to weights, the biggest strengthening of connections, happens between neurons which are the most active and the ones which we wish to become more active. In a sense, the neurons that are firing while seeing a 2 get more strongly linked to those firing when thinking about a 2. To be clear, I really am not in a position to make statements one way or another about whether artificial networks of neurons behave anything like biological brains, and this fires together, wire together idea comes with a couple meaningful asterisks. But, taken as a very loose analogy, I do find it interesting to note. Anyway, the third way that we can help increase this neuron's activation is by changing all the activations in the previous layer. Namely, if everything connected to that digit 2 neuron with a positive weight got brighter, and if everything connected with a negative weight got dimmer, then that digit 2 neuron would become more active. And similar to the weight changes, you're going to get the most bang for your buck by seeking changes that are proportional to the size of the corresponding weights. Now, of course, we cannot directly influence those activations. We only have control over the weights and biases. But just as with the last layer, it's helpful to just keep a note of what those desired changes are. But keep in mind, zooming out one step here, this is only what that digit 2 output neuron wants. Remember, we also want all of the other neurons in the last layer to become less active. And each of those other output neurons has its own thoughts about what should happen to that second to last layer. So, the desire of this digit 2 neuron is added together with the desires of all the other output neurons for what should happen to this second to last layer. Again, in proportion to the corresponding weights, and in proportion to how much each of those neurons needs to change. This right here is where the idea of propagating backwards comes in. By adding together all these desired effects, you basically get a list of nudges that you want to happen to the second to last layer. And once you have those, you can recursively apply the same process to the relevant weights and biases that determine those values, repeating the same process I just walked through and moving backwards through the network. And zooming out a bit further, remember that this is all just how a single training example wishes to nudge each one of those weights and biases. If we only listened to what that 2 wanted, the network would ultimately be incentivized just to classify all images as a 2. So what you do is you go through this same backprop routine for every other training example, recording how each of them would like to change the weights and the biases. And you average together those desired changes. This collection here of the averaged nudges to each weight and bias is, loosely speaking, the negative gradient of the cost function referenced in the last video, or at least something proportional to it. I say loosely speaking only because I have yet to get quantitatively precise about those nudges. But if you understood every change that I just referenced, why some are proportionally bigger than others, and how they all need to be added together, you understand the mechanics for what backpropagation is actually doing. By the way, in practice, it takes computers an extreme...
Okay. So let me trace it back. Okay. So he basically starts taking one example, saying out of the different examples that we want our network to learn, maybe starting point is, let's say, 2, and we say how things work for 2. If we understand that, we can generalize it for everything. So the 784 pixels go as the first input to the first neuron, and then let's say in the output we get these values. Okay, let me go a little ahead. Yeah, we get these values. So we have 0.5, 0.8, 0.2, 1, 0.4, 0.6, and so on. So what we would have hoped for, if this network was working rightly, we would have assumed we would have got close to zeros for all the other neurons and close to 1 for the neuron at 2. Okay, so we would have something like this, and that is our desire. Okay, so now since we are not getting this, there is something wrong. Okay, either with the weights or biases or activations, and we need to rectify that and we need to correct that. So we will have to provide an error to this model telling what is the right value. So the right value is this. When we provide this error, what this error should help the weights to is it should help the weights to update to a value so that we can get this kind of an output. Does that make sense? Now to get this kind of an output, several of these numbers should change. Okay, so if we just look at the 2 here, this 0.2 should increase to a level closer to 1, and the other value should go down. So he assumes that, let's say if you look at this this value next to 2 as 0.2 and this value next to 8 as 0.2, what is more relevant? Is it more important to increase this number or more important to reduce this number? So here we know that this number is already close to its answer. Okay, here it is, this number should be close to 0 and this is 0.2. This number should be close to 1 and it is 0.2. So there is more error in this number rather than this number. So like this, we would have some preference on which of these activation values do we want to modify more. Then, since this is what our understanding is, he says, let us look at just one neuron and figure out to make this neuron in the right direction, or to make this neuron closer to 1, what are the changes that we need to do. Once we understand that, then we can extend to all of these neurons. Okay. So if I go a little ahead. Okay. So you say, okay, so the value here 0.2 comes because of the previous layer. Okay. So these are the activations of the previous layer. These are the weights of the previous layer, and there is a bias term. And all these three are responsible. All these three are responsible to get this value of 0.2 here. Okay. So what are those three things? Okay. So the three things are the bias, the weights, and the activations of the previous layer. So out of these three, what are we allowed to change? Okay, we are allowed to change these biases, we are allowed to change these weights, but we are not allowed to change these activations. The activations are actually the results of when you give the input and those corresponding multiplying with the weights, you get those activation layers. Okay, so activations we cannot change, but we have a hope of what these activations should do. Now, in this case, to increase this number, we can clearly increase beta, that the bias, that is one option, or we can increase and reduce these weights. Okay, so when I say increase and reduce, what do I mean? We need to increase the weights, or let me see here. In the previous layer, we know what these values of activations are. Okay, so if I take, let's say, a bright activation like this, it is corresponding to a negative weight. Okay, now if I want to increase this number, should I make this negative weight smaller or bigger? Any idea? So, yes, I need to make this negative weight smaller. Smaller means in magnitude closer to 0. Okay, so if it is already, let's say for an example, if this is -2, then I need to make it closer towards 0 rather than -5. Okay, so because this is connected to a positive weight, if I reduce the weight of this value, then it will reduce this final number lesser, and then I will go upper, right? And the ones that are connected to high weight, so like this one, I need to increase this weight further. So these weights we have in our hand, and we have some level of intuition on what we should do with these weights. Do we increase them or do we reduce them? So that will be just using this one example, we have a hope of changing these weights up and down. Okay. Okay, let me go ahead. Yes. So now once we have these values of updates, that is for each of these activation layers, we have some hope of what we need to do. Okay, do we increase them or reduce them? That is now talking about the third part. Now remember, the third part, we cannot change the activations, but we can control what happens in the previous layer. So if we have some idea of what these weights should do, should they increase or should they reduce, we will just note these values, and using those, okay, maybe we'll discuss one other part and then come to this part. So for just one neuron, we know what we expect from all of these activation layers. Okay, but we don't just have one neuron, we have 10 different neurons at the output layer. So each neuron will have their preference. This neuron would say, I want to reduce this number, and to reduce this number, what is it expecting from this from the previous layer? So you will take its preference, then you will take the preference of the first neuron, preference of the second neuron, and so on. Okay, so throughout all the neurons will have their preference, what they want from the previous layer, and we'll average all of these out. Okay, and once we have averaged all of these out, we say, okay, these are what we expect in the second to last output layer. Because of what we expect in the second to last output layer, we can apply the same strategy one layer behind, and we can say, okay, this is what we expect from the hidden layer before that. Okay, so exactly the same strategy. You could imagine at this point that these are your output layer and these are your second last layer, and to get these outputs, what should be here? Okay, so we are propagating it backwards, right? From the output layer, we came one level back. Now from this layer, we are giving one level back. That is why it is called backward propagation. Okay, and once we do that, we will have a set of updates for this variable 2, right? But that variable 2 is not our only training example. What we want to do is we want to learn weights and biases for all of the training examples. So for 2, we have seen what are the changes it wants. For the 5, we will see what are the changes it wants. For 0, we'll see what are the changes it wants. In fact, for all the examples that we have, we will check what changes they want, and ultimately we'll average all of these changes out so that our model does better on all of these examples, not just example of one data point. Okay, we want to do it on better for all the examples, and we say to improve on all the examples, these are the updated weights. These are the gradients that we expect to change. Okay. And once we have those gradients, we can then, with some factor, which he'll talk about shortly, with some factor, we'll talk about these changes updating our previous randomized weights. And over multiple iterations, what would happen is our weights would then get modified in such a way that all of the weights will help us categorize all of these images well. So this was probably the heart of exactly how backpropagation works. Have you understood this? Do you have any questions regarding this point? Okay, great. So we'll go ahead. This is just understanding the intuition behind it, and the math, I think, comes in the next class.
Get quantitatively precise about those nudges. But if you understood every change that I just referenced, why some are proportionally bigger than others, and how they all need to be added together, you understand the mechanics for what backpropagation is actually doing. By the way, in practice, it takes computers an extremely long time to add up the influence of every single training example, every single gradient descent step. So here's what's commonly done instead. You randomly shuffle your training data and then divide it into a whole bunch of mini batches, let's say each one having 100 training examples. Then you compute a step according to the mini batch. It's not going to be the actual gradient of the cost function, which depends on all of the training data, not this tiny subset. So it's not the most efficient step downhill, but each mini batch does give you a pretty good approximation, and more importantly, it gives you a significant computational speedup. If you were to plot the trajectory of your network under the relevant cost surface, it would be a little more like a drunk man stumbling aimlessly down a hill, but taking quick steps, rather than a carefully calculating man determining the exact downhill direction of each step before taking a very slow and careful step in that direction. This technique is referred to as stochastic gradient descent. There's kind of a lot going on here, so let's just sum it up for ourselves, shall we? Backpropagation is the algorithm for determining how a single training example would like to nudge the weights and biases, not just in terms of whether they should go up or down, but in terms of what relative proportions to those changes cause the most rapid decrease to the cost. A true gradient descent step would involve doing this for all your tens and thousands of training examples and averaging the desired changes that you get. But that's computationally slow. So instead, you randomly subdivide the data into these mini batches and compute each step with respect to a mini batch. Repeatedly going through all of the mini batches and making these adjustments, you will converge towards a local minimum of the cost function, which is to say your network is going to end up doing a really good job on the training examples. So with all of that said, every line of code that would go into implementing backprop actually corresponds with something that you have now seen, at least in informal terms. But sometimes knowing what the math does is only half the battle, and just representing the damn thing is where it gets all muddled and confusing. So, for those of you who do want to go deeper, the next video goes through the same ideas that were just presented here, but in terms of the underlying calculus, which should hopefully make it a little more familiar as you see the topic in other resources. Before that, one thing worth emphasizing is that for this algorithm to work, and this goes for all sorts of machine learning beyond just neural networks, you need a lot of training data. In our case, one thing that makes handwritten digits such a nice example is that there exists the MNIST database with so many examples that have been labeled by humans. So a common challenge that those of you working in machine learning will be familiar with is just getting the labeled training data that you actually need, whether that's having people label tens of thousands of images or whatever other data type you might be dealing with. And this actually transitions really nicely to today's extremely relevant sponsor, Crowdflower, which is a software platform where data scientists and machine learning teams can create training data. They allow you to upload text or audio or image data and have it annotated by real people. You may have heard of the human-in-the-loop approach before, and this is essentially what we're talking about here, leveraging human intelligence to train machine intelligence. They employ a whole bunch of pretty smart quality control mechanisms to keep the data clean and accurate, and they've helped to train, test, and tune thousands of data and AI projects. And what's most fun, there's actually a free t-shirt in this for you guys. If you go to 3b1b.co/crowdflower or follow the link on screen and in the description, you can create a free account and run a project, and they'll send you a free shirt once you've done the job. And the shirt's actually pretty cool, I quite like it. So thanks to Crowdflower for supporting this video, and thank you also to everyone on Patreon helping support these videos.
Okay, so the main point here is regarding stochastic descent, stochastic gradient descent, and the idea is instead of taking for each update, see, we are taking multiple updates, right? For each update, we'll be changing the weights. They're saying that instead of for changing the weights, we take into account all the examples, which takes a lot of time. What we can do is we can divide our examples into mini batches, and only for this one mini batch, we identify what weight should be changed. Then for the next step, we take the other mini batch and see what weight should be changed. For the next step, we take another mini batch and take what the steps should be changed. So this increases our speed many times. The disadvantage being that now we are not traveling in a straight line from whatever random position we started to the gradient descent. So we may have maybe wrong corrections, but these wrong corrections will happen much faster. Okay, and ultimately, if this mini batch is a representative of all the numbers that we have, we would still end up with the final answer as same, but we'll reach there much faster. Okay, so it is called, again, this is a very common thing that people do, stochastic gradient descent, so that we train in mini batches, not over all of the examples, because that is very costly to do. Is that fine? Okay. In that case, let us stop here. In the next class, we'll look at the notations, and that will hopefully take us closer to implementing it in code. Okay, then we'll stop here for today.
Okay, that's fine.
Okay, see you guys. Bye bye.
Thank you. Bye bye.
Bye.